Well, hello everyone, and welcome to our Focus on Pumps session presented by ESA Pump and Vibration Specialist Gene Vogel. This session is being sponsored by Nidec Motor Corporation, and this message is provided by them. Nidec Motor Corporation, the manufacturer of U.S. Motors branded products, is proud to support the ESA education sessions today. While they are disappointed that they cannot see you all face-to-face at the convention, they are happy to support these digital training opportunities. As Albert Einstein once said, life is like riding a bicycle. To keep your balance, you must keep moving. In these times, it is essential to have open dialogue and learn from our colleagues to maintain balance and keep business moving forward. Nidec Motor Corporation will continue to keep businesses moving forward by supporting all distributors and customers. Their factories and warehouses are operating. Online ordering is available to their distributors through their e-commerce website, motorboss.com, and their sales, marketing, engineering, and trading teams are available via video chat, phone, or email to meet any of your needs. If you have any questions for engineering or want to know about the newly launched line of ID300 Fusion integrated motors and drives, their severe duty line of World Motor products, which are available in both NEMA and IEC standards, or their durable and timeless vertical hollow shaft pump motors, please reach out to them at www.usmotors.com. And now here is Gene Vogel.
Good afternoon or good morning, as the case may be, and welcome to the session on why pumps fail. If you're experienced in pump repairs, this is going to offer an organized approach to the types of failure modes that will help you analyze and understand, pumps that come in as you're working on them, as you take them apart, what was the cause of the failure, somewhat of a root cause failure analysis approach. If you're new to repairing pumps or something that you're considering getting into, this session will provide an overview in an organized format that will show you what you're likely to encounter and help you as you begin to start repairing pumps, know what to look for so you can be successful. If you have any questions throughout the presentation, please raise your hand. If you have any audio or visual problems, contact the ESA resources to help you get that squared away. There are big three, if you will, causes of pump failure. There are many other causes of pump failure, but the biggest majority of pump failures occur from these three: seal failures, impeller damage, and bearing failure. I'm going to take somewhat of a outlined approach to this, so we'll give it a real categorical, methodical approach, and that should make it clear for those who are new and for those who've seen this before in bits and pieces. The first one we're going to talk about are mechanical seals. Mechanical seal is a fairly simple device. Let me, I got one here that I'll illustrate for you. Let me see here where I find that. Now it's gone. Okay, I'm just going to, if you want to make your video larger, for the camera here, just grab a hold of the left-hand side of it with your mouse and drag it. You can get it larger. I'll hold this up to the camera, you can see it. So here's the mechanical seal. You've got a stationary element and you've got a rotating element, and each of them has a precision face, okay, which mate together. Stationary element stays still, rotating one rotates, spring applies pressure. Pretty simple concept, Here's this, if you took this seal and you cut it in half, you want to go back to the presentation, and took that seal and cut it in half.
You need to share your screen again.
Did I stop sharing it?
I stopped it for you.
Thank you. Share screen, and share. There we go. Back online. So if you took that seal and you cut it right in half, you've got kind of a diagram here. And I want to illustrate, if you want to understand how seals fail, it's important to understand how seals work. There are the primary seal and secondary seals. The primary seals are where those two faces rub against each other. The secondary seals are the elastomer that seal the rotating element to the shaft and that seal the stationary element to the housing of the pump. There we go. The stationary seat right here keeps the pumpage from finding its way out underneath between the shaft and the rotating element, and the stationary element keeps that liquid from finding its way out on that side, and that's your primary seal. Okay, so operation of the seal, it's a couple things that aren't quite so obvious. This is your primary seal, is rotating element right here. You're not seeing that. Let me get my cursor. There we go. This is the rotating element, and it has a precision face. This is a stationary element with a precision face. There's going to be a very, very tiny, small amount of the pumpage that gets in between those faces, and that's critical. That liquid, that pumpage between those faces significantly reduces the coefficient of friction between them, which reduces the heat generation. So if you've got a very thin film of pumpage in between those faces and you're rubbing together and generating some heat, some of that's going to vaporize, and there'll be a very, very tiny, a few molecules. It's not measurable. You can't smell it. The EPA can come along with a sniffer and they can pick that up. But that's the only way you can tell it. So it's not visible, you can see it, but it'll be a very small amount. Now that's an important part of the operation of the seal because it reduces that friction, it reduces the heat that's generated. The other aspect of this is notice that the surface of the rotating element and some of the surface of the stationary element is exposed to the pumpage. The pumpage is actually going to take that heat through convection off of those elements and prevent them from overheating. If you run a pump dry, you will not have the liquid in between the faces. You will not have the contact for the convection cooling, and your seal will burn up in a matter of minutes at the most. So the liquid is important for the seal operation. These are some failures. The first one is actually the normal wear. Normal wear is, you can see a wear pattern on here where the rotating element is rubbed up against the stationary element, but it's smooth, it's still shiny. There's been no abrasion, there's been no damage to it. That's what you hope to see. This is not good. This is abrasion wear. This is abrasive wear. That groove in there is not supposed to be there. That groove is worn down because there was abrasives in the pumpage. Okay, this is corrosion. Corrosion's eating that seal face up. There's something about the chemical that's being pumped, and the chemical said, now I'm going to have that seal for lunch, and it started eating it. And this is what we call heat checking. That's a particular pattern that shows up when a seal has been overheated, particularly if it's been run with too much tension. On the spring. So you can analyze the seal by looking at the seal faces. There's more to it than what I'm showing you here. There's 4 common examples. There's about a half a dozen more that I could show you. We'll limit that just to say that as far as the primary seal, if you have a seal that's leaking, why does seal leak? Take a look at the seal faces and see, is there any damage there that would indicate why the seals had leaked? If there's no indication of damage to the seals, says, gee, the seal looks good. I had one member had changed the seal out 4 times. I said, what do the seals look like? He said, they look great. I said, well, the problem's not the seal. It's somewhere else. One of the other places you look is at the secondary seal. These are the elastomers that seal, in this case, this is an O-ring that could seal that stationary element into the housing. It might be an O-ring in the rotating element, sealing the rotating section onto the shaft. A chemical attack, there's something about these O-ring material. It could be just unirubber and they're using some sort of solvents that they're pumping in the chemical they're pumping, and it absorbed some of those solvents. This smaller O-ring is the correct size. The larger O-ring should be the same size as the smaller, but it has swelled up and it'll be really spongy and soft. It will not seal. So that's a chemical attack. Someone damaged this putting it on there. They slid this O-ring up over a shaft where there's a keyway, or over a shoulder in the shaft that had a sharp edge. There's ways you can prevent from doing that. Take a little Mylar paper, wrap it around the shaft to prevent that from happening. This is the elastomer that seals the rotating element to the shaft. And you can see it's cracked and brittle from being overheated. These are different materials. There's some real expensive stuff out there, Calres, that they can make this out of. There's others that will withstand the heat better. So if the material for the elastomers is not compatible, or it's been mishandled and misinstalled, that secondary seal will fail. So if the faces look good, look at the secondary seal. If the faces look good and the secondary seal looks good, you might want to look elsewhere. The gentleman that I mentioned that had changed the seal out several times, they found that there was a leaking valve, and the pump, the water was running down the pipe onto the pump and dripping off the bottom of the pump. They changed the seal out 4 times because the valve 3 feet away was leaking. Such are the things we encounter. So what commonly causes a seal to fail? Heat is a big one. A seal overheats. Abrasive pumpage, or pumping something that's got debris and things in it and it gets in between the seal faces, that's another common one. Vibration, improper assembly, wasn't put together right, or chemical attack. Let's take each of these, let's break them down a little bit, take a little closer look, okay? The amount of heat that's generated is a function of the surface speed. The amount of force that's pressing the 2 seal faces together, and the friction coefficient of the face material. So those 3 things. The surface speed in turn is a function of how large is the seal, what's the overall diameter, how much surface area is there as a factor, and the rotating speed. So if you've got a small seal on say a swimming pool pump, it's a 1/2-inch shaft, it's a 4-pole motor, runs 1,800 RPM. The speed's not very high. You're not going to generate a lot of heat. That seal is not going to fail because of heat. But if you've got a larger piece of machinery, maybe an industrial pump's got a 3-inch shaft, a 2-pole motor running at 3,600 RPM, that surface speed's going to be a lot higher, have a little bit more surface area as well. It's going to generate more heat. The other thing is the amount of force that's being applied to those 2 seal faces, pushing them together. You got to have enough force to keep the liquid from coming out. So if it's a low pressure system, your swimming pool pump, again, for instance, there's not a lot of pressure there. You don't need a lot of tension on the seal faces. So without much tension, you're not going to generate a lot of heat. In an industrial situation, a boiler feed water pump might have 1,200, 1,500 PSI of pressure. You need to push those seal faces together a lot harder. That additional pressure generates more heat. So somewhere between the little 1/2-inch shaft, 4-pole swimming pool pump, which is easy for the seal to work, and a 3-inch diameter shaft running at 3,600 RPM on boiler feed water pump, where you need a lot of pressure, we're going to generate a lot of heat. Somewhere in between there, you're going to find a whole raft of different applications. The third thing that generates the heat, or contributes to the generation of the heat, is the coefficient of friction of the material. Now, these seal faces that I showed you here, this is carbon and ceramic. And the carbon particularly has a very low coefficient of friction. It's sort of self-lubricating. It's soft and grinds up pretty easy, so that's not good. But it will run cool. So if I'm pumping something that has abrasives, maybe it's river water coming out of a lake, or some chemical that has debris in it, those gets in between the seal face and starts grinding it up. That carbon will get ground up really quick. So they'll go with harder material like silicon carbide or tungsten carbide. But then the heat generation goes up because their coefficient of friction is higher. So you can see it's a balancing act between what does the application demand and what can I do to keep the seal cool. The last factor is how much cooling do I have? The liquid, the pumpage, is actually flowing through, a small amount of it is flowing through the seal chamber and carrying away the heat that's generated by the seal. If my pumpage is cool, swimming pool pump, you're going to have great cooling and no problems. If the pumpage is hot, boiler feed water pump pumps condensate. A couple minutes ago that was steam, now it's hot water. You're not going to get as much cooling. Chemical applications in refineries, they may pump something like hot asphalt at 700 degrees. not a whole lot of cooling going on there at 700 degrees. So that's heat. Abrasion is the other thing that damages seal faces. The picture of the seal face here, that ground right down into, that's supposed to be a flat face, is because of abrasion in the pumpage. How did I get there? That's what happens when you hit the wrong key. Please bear with me for a second. And my end key apparently is right next to my page down key. And I hit the wrong one. There we go. Let's go with pumpage. There we go. Okay. So the abrasives. Suspended solids are the most common. You're pumping sewage. And you think you're pumping water out of a lake or out of a river. You think that's pretty clear, clean water. But there is very, very tiny particles in there from the sand and other fish parts and things that are floating around in the water. I know there's fish parts. I've left some behind on occasion. So it gets in between the seal faces and grinds it up. Wastewater, liver rates, mining applications, those have a lot of debris in the liquid. Another source of abrasive pumpage is what we call crystallization. And there's lots of different applications that have crystallization. I'll focus on one that's pretty simple to understand. That's salt water. If you're pumping salt water and there's a small amount of the salt water gets in between those seal faces, when the pump stops, you've got water and salt, and the water evaporates, which means the salt forms a crystal. I don't know if you've ever seen a picture of a crystal of salt, but it's a pretty jagged looking thing. And that's what's in between your seal faces after the water evaporates, and then you start to pump up. And it grinds the faces. So these are instances where you're going to have to use something, or your seal should be designed with something different than a carbon face, because a carbon will get chewed up pretty quickly. Lots of other chemical applications that can have crystallization. Vibration is one of the things that causes seals to leak. Vibration, the typical things that cause vibration: imbalance. The impeller can be out of balance. The motor could be out of balance, causing the whole thing to shake. Misalignment, and not just misalignment of the machine, of the motor with the pump, but also misalignment of the seal parts. If the stationary element of the seal isn't aligned properly with the rotating element, you're going to generate vibration. Cavitation is something that causes problems with seals, and it causes vibration, which causes the problem with the seal. Well, we can talk a little bit about cavitation later when we get into impellers. Show you a little bit more about that. So vibration is one of the reasons that seals fail. Those seal faces are held together, but when things are vibrating and that seal starts to hop a little bit, once it hops a little bit, the liquid will start blowing through there. One of the characteristics of vibration, of a seal failure because of vibration, is sometimes they will stop the machine and restart it, and then it'll quit leaking. Until the vibration sets that seal off again and blows it open, and then it'll start leaking again. Improper assembly. You can do things to a seal when you put it together that just are going to make it fail. Obviously, we showed you cut edges, sharp edges damaging an elastomer is a fairly common one. We've seen people take and slide the rotating element up, and it's got an O-ring inside, and they didn't put any type of substance on the shaft so that it doesn't stick to the shaft, and the O-ring will actually roll up. It'll twist up inside of the rotating element, and it won't seal like that. So when you're installing elastomer parts and they need to slide over a shaft or slide into a housing, one of the things you don't want to use is grease, or in some cases oil, because it lubricates between the elastomer and the shaft, or between the elastomer, but especially between the elastomer and the shaft. And it doesn't go away, it stays there. So now you start it up and the shaft is trying to twist this rotating element and get it up to speed, and the shaft will spin inside of there because of the lubrication, and it'll start to wear and fret the shaft. It'll damage the shaft, okay? Some of the seal manufacturers make some special materials, some lubricants that are water soluble used for water pump applications. And a very good one that's easily available is KY Jelly. KY Jelly is a water-soluble lubricant. You can use it to slide parts on the seal onto the shaft, or slide the stationary element into the housing. As soon as the water comes through the pump, it's going to wash it away. So that's a little heads up there on a product that'll get you out of trouble. Let's see. There's a stationary seat, and let's take a look at the video there, Matt, if you could. If this stationary seat is not square with the rotating axis, okay, if it's at an angle, then as this rotating element turns, it's got to keep twisting to adapt to that relative to the rotating axis, and that will generate vibration and cause the seal to leak. So it's important that stationary element be put in there flat, which means that the housing that it has to go in has to be machined properly and be concentric and be flat. So there's some things to take a look at when you're thinking about repairs. Go back to the presentation. Do I need to do that?
You do.
Share screen. Got it now. We got it working now. Screen 2. Screen 2. Share. Okay. Rotating element stuck to the shaft. We just talked about that, and using the KY Jelly to prevent that from happening. The rotating element, you know, if you don't use you've got a spring trying to push it closed. If it sticks to the shaft, it doesn't close up all the way.
Hey, Gene, you need to click in PowerPoint because your slides aren't advancing.
Thank you very much. Improper seal tension. If you don't have a lot of pressure on the pumpage, you don't need a lot of seal tension. If you've got a lot of pressure on the pumpage, you need more seal tension. So the seal tension is generally set according to the application. We don't have time to go into all of that right here today. If you have some questions about that, I've done some webinars on it, and we'll probably do webinars in the future that give more details on properly tensioning seals. And the seal faces can be damaged. These seal faces are very, very, very smooth, smoother than anything you can put on it in your service center. These are lapped on a lapping machine. A seal supplier who's a value-added seal supplier will likely have a lapping machine. You would never relap a small one like this. You just replace it. But if you've got a 3-inch or 4-inch seal, very expensive, they'll relap those surfaces. So you need to be careful to preserve that smoothness. Keep the dirt off of them. You don't wipe them off with a shop towel or anything like that. You keep them clean. You can always rinse them off with some water. Okay. Chemical attack is another common cause of, not so common, but it causes problems. And we showed you the instance of the seal face, which has been corroded by the pumpage, and the O-ring, which has been swelled up because of solvents in the pumpage. Okay. All right. So that, you know, that was a really quick run through on seals. Obviously, we could spend probably half a day on seals, but to give you a little bit of an introduction of seals and how they fail, and just a couple pointers on how they don't fail. Then the second one of the big three for why pumps fail is impellers. And the impeller, you think, God, that's a chunk of metal. How does it fail? Well, the big three on how the impeller fails are erosion, corrosion, and cavitation. And it's important to be able to recognize the difference between those three. The other problem we see with impellers is that they get loose on the shaft. They don't mount on the shaft properly, and the bore gets opened up and gets fretted and worn. So we'll look at those. Let's take a look at erosion and corrosion and cavitation. Erosion is a mechanical thing. There's something in the pumpage that actually wears against the impeller and it like sands it off like a piece of sandpaper. Corrosion is different. Corrosion is a chemical reaction between something in the pumpage that ionizes and combines with the molecules that are in the alloy of the metal that constitutes the impeller. Cavitation is something which is, it is erosion. Cavitation is erosion, but it's a fairly complex condition that occurs because bubbles form in the suction and then implode. And I'll show you an illustration of that. So we need to be able to look at the differences. To do that, think of the impeller as having different inspection zones, area where I'm going to look at, specifically focus on and see what's going there, on there. One of them is the suction eye. What's going on in the suction eye of the impeller, okay? And then you have the leading edge of the vanes. That's where they intersect with the liquid, with the pumpage, and you can see a lot of what's going on at that point. You've got the vane passageway where the liquid goes from the vane out and then out the back. So that vane passageway is another area that you look at. You've got the wear ring on the outside that matches up with a wear ring. Not all impellers have that, but if it has one, it's certainly an area that we need to pay some attention to. It matches up with the casing ring and has a tight clearance. It's a clearance fit, doesn't touch. There's no wear, not rubbing against it, but it limits the flow from the low suction side of the impeller to the high pressure discharge side. Then you flip the impeller over on the back, and you have some inspection zones back here. You want to take a look at the outside shrouds, see if there's any damage or anything there. You want to take a look at the discharge area where the liquid leaves the back of the vane and the insides of the shroud. You've got the bore where the shaft mounts, and you've got the keyway. Those are all inspection zones and places that you need to take a look at on the impeller, and that will help you assess what type of damage that you have. Let's take a look at the difference, first of all, between erosion and corrosion. Erosion is an abrasion. It is a mechanical process. It is not a chemical reaction, but corrosion is a chemical reaction. Okay? The erosion is highly affected by the flow velocity. So if you look at the impeller in the places where the liquid is moving the fastest, at the leading edges of the vanes, across the working edges of the vanes, you're going to see more damage there. In corrosion, it's somewhat affected by the flow velocity because you got a chemical reaction going on. And if you throw more chemicals, against the alloy in one particular place than another, you're going to get a little bit more corrosion, but it's not nearly as pronounced as it is with erosion. Okay. Erosion usually affects most of the exposed surfaces. It affects the surfaces where the flow velocity is high much more than other surfaces, but usually if there's some sort of an abrasive material in the pumpage, it affects most of the surfaces somewhat. With corrosion, it affects all of the surfaces wherever the pumpage is in contact with the impeller. That's one of the key tip-offs between whether it's erosion or corrosion. See if all of the surfaces are affected. If it is, it's likely corrosion. And remember, what Murphy does to us, he likes to have both. He likes to have erosion and corrosion going on at the same time. You think, well, which is it? I can't tell. And you could have both. Oxidation is the most common type of corrosion. Iron rusts, that's oxidation. Different types of alloys, oxidize in different ways. You need to understand the chemical reactions there. One particular type of corrosion I want to illustrate for you because it's easy to spot is what we call dezincification. So I'll show you an example of dezincification. First, here's erosion. Notice the furrowing. Can you see these furrows down in here where it's actually, it looks like somebody got in there with a die grinder. It's not a die grinder, that's the abrasives in the pumpage. And it's cut grooves into the back of the vane even, and it's cut through the sides of the shrouds from the inside out. From the outside in, it doesn't look too bad, but from the inside out, you can see that it's worn. That's abrasive wear. That's abrasive wear, abrasion. Corrosion, on the other hand, affects all of the surfaces. Look at the surfaces even on the outside of the impeller. This is not a high velocity area out here, and yet look at the surfaces and how everything on there all shows evidence of the damage. That's corrosion damage. Where's the only part on the impeller that doesn't have it? The shoulder, where it's shouldered up against the shaft or up against the retaining nut in this case. And that's because the liquid isn't there. the metal is touching it and keeping the liquid away from it, so there's no corrosion. That's a key tip-off to corrosion damage. When that face right here is unaffected and all the rest of it is affected, it likely is corrosion damage. Here's a bronze impeller that's been just about dissolved. Notice, look where there's no damage, right there on that shoulder. Okay, so that damage came in from the outside in and from the inside out, and just pretty much dissolved the impeller. Okay, so this was chlorine corrosion, but there's other types of corrosion that can occur. One particular one I want to focus on is dezincification. Bronze is a combination of zinc, lead, brass, other alloys, but zinc is an important one in there. And certain chemicals, chlorine's one of those chemicals, dissolves the zinc and gets into the zinc and starts eating it away. The tip-off is this reddish color. When you've got an impeller that has reddish corrosion, obviously corrosion damage, and reddish color, that's probably dezincification. They make bronze alloys that do not have zinc in them. So if you run across an impeller that looks like that and it's going to have to be replaced, you'll want to alert your customer and say, look, you've got dezincification going on here. You're going to have to buy a more expensive impeller, at least a more expensive alloy, which doesn't have zinc in it, or it's going to continue to deteriorate like this. The red is because the copper that's in the alloy is the red color, and it shows up once the zinc is gone. There's a special type of dezincification called plug dezincification. It looks like a worm got in there and started digging holes in it. And once it gets started one particular area, it just corrodes and corrodes and eats and eats. And once it gets down into some zinc, it just keeps going and just got little holes all ground through it there. It looks a little bit like furrowing, but it doesn't follow the flow path. It follows strange patterns. And the real tip-off here is the reddish color. See the reddish color? That's the copper coming through when the zinc is gone. Okay, dezincification, a form of corrosion. Another aspect of impeller damage is cavitation. It's pretty common on pumps. Cavitation occurs. Cavitation, first of all, it is erosion, but it's caused by air bubbles, or vapor bubbles, if you want to get a little bit more technical about it. You take a bottle of 7-Up and you take our ginger ale, you take the lid off and pressure drops, okay? And the bubbles come out. So a reduction in pressure allows bubbles to form, okay? The bubbles will form in the suction of the impeller. That's the lowest pressure area. It's sucking the liquid in. As the liquid in the pumpage goes through the impeller, it builds up pressure. As pressure builds up on the air bubble or vapor bubble that's come in there, it finally gets to a point it can't take anymore, and push, it implodes, not explodes, implodes. And when it implodes, the liquid comes in with tremendous velocity and actually deteriorates, erodes a little bit off of that impeller. You can take a pressure washer and you can put it on your driveway and try and get that grease spot out. Holy cow, I got a hole. It will eat right through concrete. And it'll eat right into the brittle surfaces of a cast impeller.
We got a question. We got a question, and they want to know: is hard water considered erosion or corrosion?
Hard water is a chemical condition of the water itself and has very little effect on the impeller. It doesn't. Hard water does not erode impellers or any pump parts. It has minerals supported, suspended in it, but they are at the molecular level. They are not at the particle level. Hard water will cause deposits where it's allowed to sit, and you'll see, your water heater fills up with crud because of the hot water. When you heat it up, those chemicals tend to precipitate. They precipitate out of the water. So the answer is no. Hard water does not cause corrosion. Does not cause erosion. Does not cause erosion.
Another quick question is, they want to know, which material would you recommend us to recover the impeller if it presents some holes?
This impeller, if you see the impellers displayed here, this impeller will be repaired, and they'll use depending on what is pumping, they'll probably use some sort of a ceramic epoxy. There are a number of manufacturers. If you contact me offline, we actually did a whole webinar on this a number of years ago, and you can coat the impeller with these products, and you can restore this impeller. This impeller should not be reinstalled the way that it is. That once cavitation damage or any type of erosion damage starts, the roughness of the surface accentuates and makes the further erosion even worse because velocities get higher over the rough surface. So you really need a nice smooth surface. You'll coat this with one of the products. I don't want to mention brand names, but if you contact me offline, I can provide a list of different companies that make products. And every company that makes it makes several different versions. Some of this stuff is so hard you can't even cut it with a tool. It's got to be ground. So coatings are what's used to repair this. In severe cases, some people where the impeller couldn't be replaced, they've welded it and then coated it. So that repair process is a topic we could spend quite a bit of time on. I hope that answered your question. Better picture, the same thing. Oh, incidentally, somebody's going to look at this and say, well, you know, I could see this same thing if this was pumping sand and gravel and rocks, right? Isn't that the same kind of damage you get? Yes, it's erosion damage, but look right here. Notice that it stops. It stops right there, and over here, it stops right there. If that were rocks and sand and gravel, wouldn't that damage continue on up through the vein passageway? Why would it stop abruptly right here? That's where the pressure got high enough for all of the bubbles to have imploded and done their damage. And now they're just liquid and they go right through and there's no more damage. That is the key tip-off to cavitation. It's localized and it just stops at some point. On this impeller, it stopped further up. Actually, until it got up high enough pressure for all the bubbles to be imploded, it was almost out of the impeller. It just depends on the pressure balance and what's going on with the impeller. Cavitation, one of those top subjects we could spend quite a bit of time on, but in terms of why pumps fail, cavitation damages the impeller. There's a stainless steel impeller damaged by cavitation. Looks like somebody got in with a little ball peen hammer and beat on it. You know, stainless is tough. It doesn't erode the same way, but a little different appearance, still cavitation damage. The last portion of the impeller I want to take a look at today is the impeller bore, the fit to the shaft. Usually an impeller fit to the shaft is either a clearance or a transitional fit. So it may slide it on and off easily. That doesn't mean that there's something wrong with the bore. If it slides on and off easily, oh, we need to make it tighter. Not necessarily. What you need to look for are signs of fretting, signs of wear. If there's no wear and the shaft is fairly smooth, there's no wear on it, the bore of the impeller is smooth, the key looks good, it hasn't been working and wearing, then that's just fine. That's the way it's supposed to be. Okay. Check the fit of the key in the shaft and in the impeller. If the key is loose, that's trouble for an impeller. When a key gets loose, you can break an impeller. This worked and worked and worked and worked until it just took a chunk out of the side of the impeller because that key was loose in there. Oh my gosh, look at that. That key worked and worked and it just broke a piece off of the shaft. That's what happens when you get a loose key in an impeller. Here's a severe case. The impeller broke in two. How could an impeller break in two pieces? Look at the key and the keyway. Look at the wallowed keyway. That key in there working back and forth, and it finally worked enough to where it twisted and turned about an eighth of a turn, and just popped that impeller right in half. Okay, so that's an important thing to inspect. You want to look for the fit. Loose fit is not necessarily bad. Look for the wear. So that's impellers. The third element that we take a look at of the big three that cause pumps to fail are bearings. Now, we don't want to do a complete, root cause failure analysis presentation here in 10 minutes on bearings. So we're going to focus on those types of bearing failures that are peculiar or unique to pumps, okay? Whether it's sleeve bearings or roller type bearings. These are the ones we'll take a look at. One of the reasons bearings fail on pumps is contamination from the pumpage, okay? We have thrust balancing issues on pumps that can apply high axial thrust to a bearing and cause it to fail. On vertical turbine pumps, your bowl bearings and your column bearings are subject to erosion, and they're poorly lubricated. We'll explain about that. And also on the vertical turbine pumps, the ball bearings in the motor, which are not technically part of the pump, but they're integral to the operation of the machine, those can be subject to upthrust. So we need to be aware of that, what an upthrust is from a pump. So those are the issues we'll talk about on bearing failures unique to pumps. Contamination from the pumpage. Pumps is a wet environment. It's kind of likely that if you're pumping water, if you're pumping sewage, if you're pumping chemicals, some of that material is going to find its way up into the bearings, whether that bearing is in the pump or in the motor or whatever else could be driving it, okay? And the corrosion damage will be seen on the rollers and in the raceways. To see that, you've got to take the bearing apart. Many service centers have a routine bearing inspection for any machine that comes in. They cut the bearings apart, they look at the races, they'll get a magnifying glass out, at least a magnifying glass, if not a microscope, but usually at least a magnifying glass, and look at those raceways, look at those balls and rollers and see if there's any damage. One of the types of damage you're looking for is corrosion. Corrosion has a different appearance than does false Brinelling or spalling or the other things that cause a bearing to fail. So looking for corrosion is an important element in inspecting bearings from pumps. The bearings are right next to the seal. The seal fails, the liquid comes out, the liquid washes back up into the bearing, washes the lubrication out of the bearing, and then the bearing fails. You're trying to do root cause failure analysis, you got a bad bearing, you got a seal that's failed, which came first? Did the seal fail and wash the, what we just talked about, wash out the bearing and it failed? Or did the bearing fail? If the bearing fails, what's the chances that the seal is going to keep functioning properly? You're probably going to have the seal leak as soon as the bearing starts to fail. It can be difficult to tell which came first. There's no set way for it. So one of the dilemmas that you'll encounter repairing pumps and trying to figure out why it failed. Impellers suck liquid into the suction eye. Now, some impellers have two suction eyes and suck from both sides, and that's dandy because they don't get any axial thrust. But a large number of the pumps that are out there are simply have suction on one side, and if you're sucking liquid in one side, there has to be an equal and opposite force in the other direction, a reaction force. Does it suck liquid in, it's pulling that shaft up towards the pump. And you may take a look at some of the bearings that come out of a pump, and you'll see evidence of high axial force. And that could be because some function of the pump, which is supposed to control that axial force, has failed. Pumps may use balancing pistons, or they may have a wear ring on the back of the impeller and balancing holes. You should be able to recognize that. This is the back of the impeller. This is where the shaft goes in, okay? The suction's on the other side. Notice the holes through here and the wear ring on the back. This is the wear ring on the back. This impeller has a rear wear ring. Can you say that 3 times? Rear wear ring, rear. If you can say that 3 times, I want you to stop on the way home, buy yourself a beer. If you can say that 3 times, okay? Rear wear ring, there it is. Okay, so if these holes get clogged up, or if this wear ring is worn and the clearance is too far open, it's supposed to develop a low pressure area suction on the back end impeller that counteracts the suction from the front. If those fail, you're going to get high axial force and you're going to wear the axial wear on the bearings that support the shaft. So that's something unique to pumps. You don't find that on other types of machinery. Okay. All right. Yeah, on balancing, said that already. Looking for that's root good. Got that. Great. So vertical turbine pumps. Vertical turbine pumps have sleeve bearings in them that go down the column, and they have sleeve bearings in the pump bowls themselves. Most of the vertical turbine pumps, those sleeve bearings are lubricated by the pumpage. So if you're pumping water, it's not a real good lubricant, and it's got abrasives in it because it's coming out of a well, or it's coming out of a river or a lake or something, then those bearings are going to, that's the weak point of vertical turbine pumps, is those sleeve bearings, because they just don't get lubrication. In fact, the one that fails most often is the one way up at the top, just below the seal, especially if it's a deep well application. That pump turns on and it might run for several minutes before it manages to pull the liquid out. It could be 200 or 300, 400 feet deep, until it pulls that liquid all the way up from the bottom up to the discharge. Meanwhile, the bearings up at the top of the pump are running dry. And they probably got some abrasive left in them from the last time that the pump was running and shut down, and the water evaporated, but the abrasives are still in there. So that's a classic failure mode for these types of pumps. You can do a little bit of analysis on them. The other things that cause those bearings to fail, if a bearing is eccentric, if it's not in the middle, when you assemble the pump, you bolt all these things together and the bearings are pressed in. If somebody hasn't taken the time to be sure the connecting rabbets are concentric and perpendicular, then your bearings are going to be misaligned with each other, and you're going to see some excessive bearing wear. So if you look at the bearing wear and the bearing is worn on one side, that usually means that bearing is probably not true to the other bearings in the machine. And you can analyze that if you pay attention to how that machine was put together and the orientation of the bearings. You see this one's worn on the north side and this one's worn on the south side. It doesn't take, anybody with a whole lot of smarts to figure out that shaft's not going through there straight. On the other hand, if you look at the shaft, and the shaft is worn on one side, but the bearing is worn all the way around, then either the shaft is not running true because it's kinked or bent, or the coupling is not square, or the impeller may be out of balance if it's the bearings down in the bottom by the pump. So you can tell a little bit by looking at the bearing wear and find out what may have gone on there. There's an illustration of what I'm talking about with vertical turbine pumps. These are your bowl bearings. There's a bowl bearings here. These are your column bearings. Some of them have a web. Okay, this is enclosed. Now this is different. These bearings are enclosed, and they might have lubricant coming down through here. They might be dripping oil down through there. So that's one of the ways to get away from it. But that shaft enclosing tube is an expensive proposition when you're buying a new pump. And why would I want to spend that money? I'm not responsible for the maintenance budget. I'm only responsible for the, asset acquisition budget. So we'll get the cheap one. All right. And then you've got this over here. The only thing lubricating those bushings, those bearings, is the pumpage coming up through that column. Okay. This is not an unusual failure for a vertical turbine pump. That shaft seized up on the bearing. The bearing started spinning in the housing. It beat the housing all out. Now this will be repaired. They'll bore this out, they'll plug it, they'll press a bearing in and bore the bearing out and replace the shaft, and this will be repaired. Okay? So vertical turbine pumps and the bearings that are in them. Upthrust is an issue that needs to be understood if you're going to work on pumps. We would expect that a vertical pump would have downward force to lift the liquid up. But there are particular times, particularly at shutdown momentarily, and then at high flow rates for continuous times, where the actual force on the pump shaft is up, not down. And to do that, you'd have to look at the reaction forces of what goes on and how the water is lifted. And I pulled these slides out of another presentation where we talked about that. In fact, I did a presentation that was, a paper on this that you might want to look up. At high flow rates, 130% of capacity, your thrust becomes negative. Negative thrust on a pump means that's up. Normal thrust, positive thrust is down. Okay, so if you're going to have upthrust on these pumps and the motor is an integral part of this machine, the pump can't operate by itself. The pump shaft actually hangs on the motor shaft. So the motor bearings are what must control the upthrust. And that calls for angular contact bearings configured either back to back or face to face, or some sort of a special provision that will handle upthrust. Two tandem bearings or any single bearing in the top is going to be configured for downthrust. So you have to consider upthrust as and how the bearings are oriented as the bearings in the motor that support the pump. Another subject that requires a little bit more discussion than we have time for here. There is a paper available for that, and I think that was, in fact, I think that was a Currents article a couple months ago. So look up the ESA Currents article on upthrust if that's something that you're wondering about. Well, I hope we've covered
You have a quick
what it
question?
is that causes pumps to fail. We've left a few minutes here at the end for a little bit of questions if we have them. Seals fail on pumps. You have to know how they work to know how they fail. Okay. Primary and secondary seals might fail. So inspect the seal and see if there's any damage to the seal faces. Those look good. Well, what do the secondary seals look like? What does the housing or shaft look like where that secondary seal mounts? Okay. Heat, abrasion, vibration, improper assembly, and chemical attack are the things that cause seals to fail. With impellers, we need to be able to recognize erosion, corrosion, and cavitation. To do that, we look at impellers in different inspection zones and make sure that we understand what all the damage is in each inspection zone. We also need to look at the shaft and the keyway. With bearings, we apply our root cause failure analysis techniques. We cut the bearings apart if they're ball or roller bearings. We do a good careful inspection of the sleeve bearings and see if we can determine the type of failure mode. Pumpage and corrosion damage are common with pumps because there's so much, it's there, it's all around, it's in the bearing. The vertical turbine pump bearings you can take a look at and see how they have worn. Suction, thrust, and upthrust are unique to pumps. You don't have those on a lot of other machines. You have them on gear cases, but with helical gears, but you don't have them on all of the other types of machines that we might work on. So thrust is something that needs to be considered.
Ready for a couple questions?
Yeah.
First one is, any difference between application for a face-to-face versus a back-to-back thrust bearing?
The applications, the answer, do I need to repeat the question?
It was.
Did you hear you say the question, or shall I repeat it?
I read it. I can read it again. Any difference between application for a face-to-face versus a back-to-back thrust bearing?
Yeah. Okay. Let me get my slides going here. There we go. Okay. So I need to go to, where's my slide? There it is. Had to find it. Okay. So back-to-back or face-to-face, okay? With back-to-back, it's this upper bearing, which is taking the down thrust, and the lower bearing is configured for up thrust. If I took this top bearing and slipped it around and underneath the bottom, or if I flipped them both over, then I'd have face-to-face, okay? The application really doesn't care. what makes a difference is how the particular bearing housing is designed and how the shaft is designed. Okay. Since we're going to control both upthrust and downthrust, both the inner races and the outer races must be retained. Otherwise, the upthrust would push the shaft out of the bearings, or the upthrust would push the bearings up out of the housing, or vice versa. So they've got to be retaining on both sides. The difference is that one pair of these, either inner or outer, need to be clamped, not just retained, but clamped, so that you set the proper internal clearance or preload, as the case may be. If you've got a snap ring on the shaft, it can't clamp the inner races together. So if there's a snap ring on the shaft, they should be face to face, and that means that the outer races need to be clamped together. So whatever the bearing housing is that holds those outer races together needs to put some pressure on the outer races and clamp them to apply whatever preload or to assign the proper internal clearance to the bearing. So you have clamping force and retainers that beyond what I'm able to illustrate here with just my cursor. I've done a presentation on that, and I have some more slides. I don't have them immediately available. So investigate that a little bit further. I guess that could be called the application. I'm thinking in terms of the housing, the bearing housing and the shaft. Usually the application I'm thinking is the pump and what it's pumping. The pump doesn't care. The pump doesn't care whether it's face-to-face or back-to-back. The bearing housing is what makes that determination. I hope I answered your question.
Next question, is it only corrosion that causes dezincification?
Read the question again. I didn't hear the...
Is it only corrosion that causes dezincification?
Yes. Dezincification is a form of corrosion. Whatever the chemical is, and there's a number of chemicals that will do it, whatever the chemical is that is causing it really likes zinc, and it eats the zinc away. So you got a chemical reaction between something in the pumpage and zinc. Chlorine is one of the things that will do that.
Next question, what factors will decide which bearing arrangement to be used, face-to-face or back-to-back?
Okay, that's the same question as before, and the answer as to what determines whether they're face-to-face or back-to-back, it's the bearing housing and the shaft. Either the housing or the shaft needs to apply clamping to preload. If it's the housing, it's face-to-face. If it's the shaft, it's back-to-back.
And finally, could you repeat the tests that you recommend for the pumps?
Which tests? Read the question again.
It just says, could you repeat the tests or all the tests that you recommend for the pumps?
Well, I'm probably not understanding the question, but pumps can be tested operationally by hooking them up and see if they pump water. If it's a submersible, you test the seal chamber with about 12 to 15 psi of air after it's been filled with oil. So there's probably some other type of test that he's asking about. Okay. She is asking about.
This one just came in. Can shaft currents caused by VFDs work their way through to the pump and react to water chemical makeup or even mineral makeup?
Yes. There's a number of different types of corrosion. The most common type of corrosion is ionization, caustics and acids, and those do not involve any flow of electricity. But there's galvanic corrosion, which will actually generate, galvanic won't generate, electrolysis, which will generate an electrical flow, and galvanic corrosion, which occurs when you do have voltage potential across dissimilar metals with an electrolyte. It has to have an electrolyte, and you have to have a voltage, applied. So if your VFD or any other source, it doesn't have to be a VFD, just poor grounding. just poor grounding can result in a voltage source between the pump and some other dissimilar metal. If you got salt water or anything else that you're pumping that is an electrolyte, you get electrical flow and you'll get galvanic corrosion.
Is there any chemical in well water that causes dezincification?
I don't know. I honestly don't know. I don't know what they pump out of wells. When you say well water, I will tell you this: I've never seen dezincification on a water pump. It's always been on chemical pumps. So my guess is, just from my experience, the answer is probably no. But I honestly don't know the answer to that.
Is a fire pump different from a standard industrial pump?
Only when it's burning. No. No. The pump itself, they're not. They paint it. They paint them red. Some companies paint them red. But there's really no difference in the pump from a fire pump or any other. And the regulations that are applied to fire pumps are applied by the local government authority, whether that is the city, the county, the municipality, the township, whoever it is, the fire department takes care of that. So it varies. And I couldn't say that there isn't some location, some place where somebody's got a regulation that tells you the pump needs to be painted red, or that the pump can't have this or can't have that. They certainly could do that. There's nothing stopping them. I don't know of any.
All right, that's
Other
it.
questions?
You're good.
All right. Well, at that point, then we're going to we'll take 2 minutes, a 2-minute break, and when we get back, we will jump into the next presentation, which is on trimming impellers. So 2 minutes.